Today we will start the new module. We will discuss the physics of molecules. You will see that we are making gradual progress in understanding more and more complex systems. So we started off with hydrogen atom, and then we had many electron atoms, so helium, lithium onwards. At that time, we stressed it 2 points. First of all, we know the physics. That is to say, we can write down the governing equation. No problem. So we know the governing equation, but any atom, including helium, the governing equation is just too complicated to solve. No one can solve it analytically. And therefore, we have to look for clever ways to handle the difficult situation, especially the difficulties arising from the electron-electron Coulomb interaction. And then we had this very clever ideas of taking into account of n-1 electrons effect on one electron, reduce it to a single electron problem, and solve the atomic orbitals. The next step is that we have some rules to fill the electrons into this single electron atomic orbitals, namely the power exclusion principle, behind which is the antisymmetric requirement of many electron wave functions. And today, we will look into a class of even more complicated problems. We have 2 nuclei, at least. There could be many bigger molecules, but diatomic molecules will be the focus of our discussion to bring out the key ideas. So at least we will have 2 nuclei and some number of electrons. So it is even worse. Previously, in sodium atom, we have 1 nucleus and 11 electrons. That is already very difficult. But today, we started to study system with several nuclei and many electrons. So first of all, I would like to again express the fact that we know the governing equations, but the problems are more complicated than the atomic problems in a fundamental way. And I would like to first make it clear what kind of questions we want to answer. And then I will show you that we know the governing equations, very long, Schrödinger equation, and then we try to understand the difficulties. And after you understand the difficulty, then there may be some hints on finding a way out, meaning trying to develop some useful approximations. So that will be the first part of this module, all right? So let me start. It is good to do it after the midterm, so at least I hope that the background knowledge will be very fresh for most of you. So in this module, we will be discussing a main topic is the quantum mechanics of chemical bonds. That is to say, if we have several nuclei, say 2 nuclei, H2 molecules will be the simplest molecule to consider. But let me tell you at the outset, even H2 cannot be solved, okay? So don't feel bad. I mean, cannot be solved analytically. So that is already the simplest molecule. Therefore, one may make whatever approximations we would like to make, and we will judge the usefulness by the outcomes. So the problem is, if I have 2 nuclei or 3 nuclei, if you are the electrons, then there is a question. how would you distribute, that is to say your wave function, okay? So how would the electron distribute themselves so as to hold this entity together? A molecule means these three atoms are bind together. Okay, so this is already a rather fascinating question. If you think about it, give you three atoms, what should the electrons do? And that is a key question that we will explore. The problem is we have a rather complicated Hamiltonian, but we know how to write it down. I will show you 20 pages later what is the Hamiltonian. The Hamiltonian consists of electrons and nuclei. So the problem is that in hydrogen atom problem or in other atom problems, we have only one nucleus and we can take the nucleus to be fixed at 0, 0, 0, okay? And then use the reduced mass and then everything becomes okay. That is to say, in terms of very deeper physics, the center of mass motion of the atom is not our focus. We remove that part, introduce the reduced mass, and then the nucleus becomes a fixed point particle at 0, 0, 0. We only have to deal with the electrons. But in molecules, we don't have that luxury. Even if you use reduced mass, you can only fix the location of one of the two nuclei, and then you have this relative motion remaining. So, in addition to the electron problems, unavoidably, for molecules, we have a nuclei motion problem. So that is concept number one. By that I mean, you need to appreciate the complexity of the molecular problems. There's another dimension and other classes of questions to ask. After we know how the electron distribute, we still have to worry about the vibrational motion of the two nuclei, and the whole molecule could rotate. Now, that is something, these two additional motions are something that we don't need to worry in atoms, okay? So this is what I depicted here. This will be called the internal degrees of freedom of the molecules. Even if we know the electron's behavior that is responsible for bonding, then we have these two nuclei connected by a bond. They could vibrate, the whole molecules could rotate. So certainly it is more complicated, but not that complicated as you may think, because if you think about vibrational physics, it is nothing but oscillator physics. So you are all well trained in harmonic oscillator, right? And then for the rotational problem, it is just the rotor problem or rotator problem in quantum mechanics. You know the solution is something like YLM theta phi, okay? So if you think deeper, there may be some comforts coming out. Okay, it's not that new, you have development background, okay? So take home point number one, more complicated because we have electron problem plus nuclei motion problem. So further illustrate it is a harder problem than atoms. There are two main questions that we want to find the answer. Number one, let's say given the two nuclei are at some locations, so there is a certain distance apart. Question number one is, for the electrons, they will ask, what should we do? That is to say, what should be our wave function? For which wave function square will give us how the electrons distribute themselves so as to bind the two nuclei together to form a molecule. Okay, so that is question number one. Well, it is not entirely new quantum mechanical problems. Worse and worse, I have, for example, 3 electrons here and 11 electrons there. So altogether 14 electrons. So it is like a multi-electron atomic problem after all. Then maybe we can use the idea of reducing it to single electron Schrödinger problems, solving for single electron states, and then fill them in by Pauli exclusion principle. And that is, in fact, the strategy. The single particle states here will be called molecular orbitals. Rather naturally, right? For atoms, we have atomic orbitals, 1s, 2s. For molecules, we are going to solve for some single electron states called molecular orbitals, or in short, MO. Okay, so that is the strategy for the question on the left-hand side. But even worse, we have the questions on the right-hand side. If you are the nuclei, 2 or more, then you started to ask, where should we sit? There's different separations, right? So perhaps R1, or closer R2, or farther away R3, that should be R3, okay? So for the nuclei, they are wondering, what is the best separation? And for those who have learned a little bit of chemistry, for molecules, there's something called bond length. That is characterizing for CO bond, you have a certain bond length and so on, okay? That is the preferred separation. That is the length, the separation that you will find experimentally. That is to say, you look at the molecule, the nuclei prefer to sit there at that separation. What is determining this preferred separation? Now, keep this question in mind. The answer is rather wonderful and fascinating. Okay? And then if the nuclei know what is the best separation, so there's a preferred separation, then comes the problem that I already pointed out, vibration and rotation, the nuclei motion problem. Okay, so first, these 2 pages appreciate that we are handling something highly non-trivial. Then I hope as we go, you have a further appreciation that with the quantum mechanics that you learned up to this point, we can go very far in understanding molecules. And that is a wonderful piece of news, right? So let's meet some molecules so as to get a sense of the scope of our discussion. Molecules can be simple. So this carbon dioxide happens to be a linear molecule, but now regarded as a bad guy for climate change, things like that, okay? So we will understand why suddenly this innocent molecules become a bad guy. And then this is water. Again, only 3 atoms, but extended at a certain angle. So we will also look into why the certain angle, things like that. Again, water vapor is also not a good guide in terms of greenhouse effect. And then we have this organic molecule, propane. So you have a lot of this kind of things. And carbon with hydrogen give you a lot of funny things. Not only this one, for example, you have CH4, and that will be a wonderful place to study hybridization, something that you might have heard before. And then we have this carbon hydrogen thing again called benzene. And in particular, very often you see a circle inside this symbol. Then what is the quantum mechanics behind this circle? Okay, so we will find that you need to go into university and then go rather deep into quantum mechanics in order to understand this circle. Although many chemists draw it, and I don't think they understand it fully. So even simpler one that we will often use in our discussion are the diatomic molecules. Molecules formed by only 2 atoms. Okay, nothing can be simpler than that, especially H2. That is the simplest neutral molecule. Because we have some molecular ions that can be simpler, you take out an electron to make the molecule becomes an ion. Okay, for example, the simplest thing is H2 plus ion. Now that is the simplest thing. You have 2 nucleus and 1 electron. Because you take out an electron, ionize it, okay? Now, for all students here, you may start to think about what should you do if you are the electrons. 2 nuclei, 1 electron. How could you work out to keep the 2 nuclei in place? Okay, you have to be rather busy, right? You have to bind the left one and bind to the right-hand side one so that these 2 will be happy and stay there. Okay, experimental fact: H2 plus ion exists. So we have some physics to explain. And when we understand that, we will see that even that simple system, the binding is highly quantum mechanical. We cannot avoid, okay? In the past, in high school, you have this weight statement. The electrons live somewhere in the middle of the 2 nuclei, so making use of the Coulomb attraction to the left, to the right, everybody is happy. Well, I would say those statements are so cleverly crafted, so vague that you cannot say they are wrong, but they basically, you don't know what they are talking about. I hope that after our discussion, you have a better sense of what these very base statements are about. It's talking about the wave function and the wave function square, how they distribute, and the consequence of that distribution give us the picture of a particular name called covalent bond, things like that. And here is a product that you can buy in the pharmacy. DHA to make help people to be cleverer. So it's a long chain of carbon. There are 22. Then you start counting backwards 3. So 22nd, 21st. Okay. 22nd, 20. Okay. 22nd, 21st, 2019. Okay, so this one. And then between this one is a double bond. Okay, so you have a big class of things, a long chain, you count back 3, and then you have a double bond. Those are collectively called DHA. Why they could help you to become cleverer, I don't quite know. but this is the product, okay? And then, for example, our life depends on very big molecules, the DNA. So we have a group of atoms forming something called AGCT, and then they bind together, okay? A goes with T, G goes with C, in a rather weak bonding, something called hydrogen bond, okay? And then that will be good. We don't need to spend much energy to break the two chain so that they could replicate rather easily. Otherwise, we need to eat a lot of things. So here comes a second key concept: things that bind. All right. So first of all, take in the fact molecules exist. That is to say, CO2, they do bind. The three atoms do come together to form a rather stable molecule. And then there is some preferred separation. This is an experimental fact. Even benzene, you can look up what is the CC bond, and then there is a preferred separation. Okay? Now, exercise your physics common sense. By the very fact that they exist, that is to say, this thing become more stable when they form this entity. Okay, they have a choice. Carbon and the two oxygens could just separate into neutral atoms, don't care about each other. That's one choice. Second choice, come together to form a molecule. Okay? The fact is that they exist. So you can think about that in this form, the energy should be lower than the three atoms, the neutral atoms apart. Okay, so exercise your physics logic. Then secondly, there is a preferred bond length separation. Okay, so now combining these two facts, we have a rough picture about the potential energy function as a function of the separation between the two nuclei. By preferred, it means the following. Closer is not happy, so energy will be higher. Farther away, not happy, will be higher. So immediately we have this sense. When something binds, this function of the energy versus the separation between two entities should have such a minimum. This is the best place, so that that distance will be the preferred separation. And then if there is a reference point of energy referring to neutral separate entities, you can define that as zero. It doesn't matter, it's relative. And then you know that how deep this well, okay, I call it a potential well, how deep this well is would represent how much energy is gained by forming this binded entity. Okay, so take home message. When you see something bind, say two things bind, this is something that you should think about. There is an energy function versus separation with a minimum, okay? And now, go ahead in thinking, near the minimum is like a harmonic, is parabolic, so it's like harmonic oscillator, thereby there's some vibration motion when we discuss the two nuclei vibrating relative to each other, okay? So when there are things bind, think about this, okay? Well, it is not only for molecules. We have seen several things that bind. Electrons bind to a nucleus to form an atom. We are considering atoms bind into molecules even in the nucleus, we will see that proton, neutrons bind to form the stable nuclei. What for? When that occurs, think about this one. Okay? Doing so, if this curve exists, there will be some energy gained. In other words, for a stable binded thing, you supply this kind of energy, you will be able to break them apart. This is called the dissociation energy. Okay? So nothing profound, just exercise our logic. Then, if the third point in our introduction, what is the energy scale that we are talking about for this binding? When we write down the Hamiltonian, we see that what is really important there is just Coulomb interaction. We have nucleus plus charge, we have electrons minus charge. So every electron see nucleus A, nucleus B, and then all the electrons see each other repel. The two nuclei see each other, they also have Coulomb interaction. So Coulomb interaction is at the heart of binding. You don't have other fancy stuff, right? You don't need strong force, you don't need weak interaction. It is electrodynamics. So given that, we can, in one line, estimate what is the energy scale that we are considering, right? So Coulombic, so E squared over 4 pi epsilon 0, and then divided by a typical distance. What is the typical distance? Separation, equilibrium preferred separation. If you look into data, that number is very boring. It's often go from less than an angstrom to about 2 angstrom, something like that. So 1 to 2 angstrom is the right ballpark. Very far away, the two atoms will not care about each other, okay? I think you have this sense. Hydrogen, the electron is in 1s. 1s, the Bohr radius is half angstrom. If the two hydrogen atoms are 10 angstrom apart, the 1s wave function is exponentially decaying. So this wave function decays very quickly to 0, and then the other one also decays very quickly to 0. That is to say, this atom does not sense the other atom's presence. They have to touch each other, the wave function, the tail, in order to know, there is something there. Then they can start thinking, should we bind? If we bind, we gain some energy, let's do it, okay? But if they're so far apart, they don't even sense each other's presence, nothing will happen, okay? That is very much, well, this is high-level quantum mechanics common sense, okay? It's not entirely common sense as a layman. So with that, you can easily estimate what is the ballpark energy we are dealing with. Plugging in 1 to 2 angstrom in the denominator, we are handling energy scale of a few eV, a few electron volt. Nothing surprising, this is the atomic scale. You use atoms to form molecules. So this binding must be of the same order of magnitude, okay? Now, for those who like numbers, there is no reason why every time you use your calculator to plug everything in again and again. So here, I give you a number for this very common combination. It is 1.44, well, you can take it as 1, okay? EV nanometer. And angstrom is 0.1 nanometer, okay? Therefore, if you have 1 angstrom, you multiply this by 10, then it is 14.4 EV, all right? So here I plug in maybe 2 angstrom, that is, it gets to 7 EV. That's about the ballpark range. The following minutes has nothing to do with molecular physics. I'm just trying to point out that even when we are dealing with nuclear physics, when you have 2 nucleons bind together, we are still looking at this curve. So you can imagine this is the energy versus neutron-neutron separation, okay? And then you have this shape because they bind in the nucleus. But only that, the preferred separation will take on a different length scale. That will be 10 to the minus 15 EV, meter, sorry. Because nucleus is of this size. And then the energy scale involved in binding will be MeV. Okay? Because we know from nuclear, those decays, the things that come out, alpha particle, or those is of this scale, MeV. Nonetheless, the shape is something like that, okay? So now we have, you must have heard some many terms in terms of molecular binding. You might have heard about ionic bond, covalent bond, metallic bond, electron freely moving, hydrogen bond, van der Waals bonds, things like that, okay? We will look into this kind of bonding, but not with the title that, now this section we will consider covalent bond, okay? That is not our concept. The concept actually has to do with, you solve the Schrödinger equation first. Then you see how the electrons distribute themselves. And then you look at the result. If the electron prefer one atom than the other, that is to say, the electron moved it from one electron to the other, the two things form ions, then you have ionic bond. If the distribution is more or less very fair between the two sides, then you will have covalent bond. It is a result rather than predetermined thing. We are talking about covalent bond. It is not it's not an educated way to do it like that, okay? So this is the point I want to point out. We already point out that there are 2 quantities very often cited. Bond length, that is the preferred separation, and binding energy. That is the energy that you need to provide in order to break them apart into neutral atoms, okay? Or in other words, neutral atoms come together, when they form, they will release this binding energy, okay? Or gain this binding energy. So here I just give you some numbers so that you know the ballpark number. Very boring numbers, actually. Nothing vary by a big range. But that's good, okay? So you see, I give you some typical, people will call it ionic things, and then we have some covalent thing, okay? And then this also covalent thing. For those who know chemistry, you will have double bond, triple bond, all these funny terms here, okay? Nonetheless, look at the preferred separation. It is now in nanometer. If you shift the digit by one place, that is angstrom, okay? So that means 0.74 angstrom is the preferred separation for the smallest, simplest molecule. But other than that, usually it's 1 angstrom to 2 angstrom, okay, this digit, all right? Binding energy wise, well, EV, okay? Remember this? And then, well, very boring. 1, 2, 3, 4, 5, that kind of number. But if we have hydrogen bonding, that is a weaker bond. That is to say, you don't need EV energy to break them, okay? And that is good for our life. So this is what I just said. Ionic, covalent, everything has to do with the wave function of the electron squared, okay? If it goes to one side, then atom A looks like, if the electron goes to one atom nearer to one side, so A becomes, take in one more electrons, become an anion, so-called chemist, and then the other cation, and then you have ionic character, right? Otherwise, if it is does not prefer any side, you will call it covalent. So the message is that quantum mechanics will put bonding, this topic, under one umbrella, one roof. Just solve the quantum mechanics Schrödinger equation. That's it. Okay? You don't need to pre-decide. This is covalent, this is ionic. Here is the picture, all right? So you solve the Schrödinger equation. At the end, you know how the wave function behave. Then we can discuss, is it ionic with some covalent character or covalent with some ionic character? Actually, these are the most common situations. Instead of 100% ionic, 100% covalent, that is not usually the case. So that ends the introduction. The second part, we will just do something simpler than quantum mechanics. We will do some energy accounting. Therefore, we will not see Schrödinger equation, things like that here. I just want you to get a sense that this binding curve can actually come out rather easily, okay? Then we go into quantum mechanics and see how this binding curve can arise. I call this part energetics, meaning energy accounting. I will use this ionic compounds. At the end, we know that it's rather ionic to do the discussion. There are some knowledge in atomic physics here being used. The idea is as following. Ionization of an atom needs energy. So we have heard about the ionization energy of an atom. Okay? So for example, here, the first page, I consider lithium fluoride. The same goes to sodium chloride. Group 1, group 7, that is the most ionic stuff. Start with neutral atom. First question, if there is a charge transfer, meaning the 2s1, that electron rather lonely out there, go to the other side to become a fluorine minus ion, okay? How much energy is needed? That is the question, okay? Here, there are two energies involved. We discussed them in atomic physics module. One is the ionization energy. How much energy you need to take this electron out of lithium, okay? That is the ionization energy. Second is the electron affinity. This is the energy gained for some atoms. If you put one extra electron into it, the total energy, the ground state, could actually be lowered. And the amount is called electron affinity. Just to remind you, to calculate the ionization energy quantum mechanically, you need to do two calculations: neutral lithium and then lithium plus iron. Compare the energy difference, then you know how much energy is needed. Similarly, for the electron affinity. So here I give you the first big picture. Neutral atom, you ionize lithium, you need some energy. The electron goes into fluorine, you may be gaining back some electron affinity. Whether the accounting is positive or negative depends on the value. Most of the time, you need a net energy to form the two ions. Okay? But after that, you started to gain something back. Neutral atom does not have Coulomb attraction. Become ions, they Coulomb attract, and the Coulomb attraction energy is negative. So they gain back some Coulomb attraction energy. So there is some accounting to do. So here is more concrete numbers. Sodium, ionize it, look at tables, you need 5 eV. To make it an ion, pull an electron out, okay? Then this electron to go to the chlorine, give it, you gain back some electron affinity, but only 3.6 eV. You give in 5.1, you gain back 3.6. That is to say, in order to go from neutral sodium chloride atom into a sodium plus chlorine minus, there is a net energy required. Okay? So take this point, and then that means this charge transfer will not occur spontaneously, automatically. Okay? But then, why does it happen? We do have salt, sodium chloride. There is a consequence after ionization. There is some Coulomb attraction gained. Okay? At the end, there will be a preferred separation. Then we can calculate what is the Coulomb attraction energy, and the net is that the energy is actually lowered. So let's look into the curve. We just saw that we need energy to form the two ions, okay? But then we gain back some attractive Coulombic energy that is a function of the separation. So this energy required is constant. This will be more negative when the two ions comes together closer, okay? Now you may think they should come closer and closer and closer, so you gain a lot of Coulomb energy, okay? On the surface, it looks like that, but remember, there are still 10 electrons here, quite a lot, okay? And then there are, I don't know, 20 electrons here. When these two crowd of electrons comes together, they don't like each other, several reasons: Coulomb repulsion, nuclei repulsion, and more. The exchange term that has to do with similar spin electrons don't like to be at the same place due to antisymmetric or Pauli exclusion principle. Okay, so let's put these two things together for the moment. 1.52 eV, you gain back some Coulomb attraction. So here I plot it. The zero here is neutral atoms. Define it as zero, okay? That's why there is a positive energy, 1.52, this line, okay, constant. That is the energy required to form two ions. Then this axis, horizontal x-axis, is the separation. When they are very far, there's nothing good about it. The Coulomb attraction does not compensate this. But there is a break-even point. I label it RC, a critical separation, under which there may be advantage. Okay? Only below this separation, the Coulomb attraction gain back what is put into the neutral atom to form ions. Then, will this continue to go down to negative infinity as this thing suggests? But I already hinted at no. When the two ions come too close to each other, there is always a very strong core repulsion. There are many reasons for that. The two nuclei also have some Coulomb repulsion. They are same charge. That is one factor. And actually, more importantly, the electrons in the ions, when they start to occupy the same region, they are more quantum mechanical effective repulsion. I think you have done your homework, right? So you plot those two electron and two particle wave function. That is the effect. They tend to avoid each other, okay? And at the back of this, actually, that has to do with filling in some molecular orbitals, and they repel each other. So at the end, the net effect is the following. We have seen these two terms. There is always a very strong core repulsion part. This part at this level of discussion of ionic thing is usually treated phenomenologically, using experience or experimental fact. It is very steep. So it goes like plus, meaning repulsion, a constant 1/r to a very high power. This n usually is something like 9 or above. Okay. Again, it's empirical. No theoretical reason for a particular number. Usually it's a fraction, a 9.5 or something like that. But it represents the very steep, strong repulsive force. So let us put these three things together, okay? So look at these three terms. A constant 1.52, a Coulomb attraction, and a very strong repulsion. This continue to go down, but very strong repulsion, okay? So you see, you add up all this, at short separation, this will dominate. So here, repeat the same graph, a constant, the second term, and a very steep repulsive. At the end, you see the thicker line. Okay, follow me? It's thicker line, all right? Now, this very thick line is exactly what we motivated at the beginning. Two things now bind, okay? You see this curve. And from this curve, we can read out two numbers. There's a minimum in energy, therefore there is a preferred separation. Okay, you read that out, you know that it is 2.36 angstrom. Second point, you can read out the depth. Now be careful, 0 is the energy of far apart neutral atoms. That is our reference energy. It is not this higher horizontal line where this refers to two well-separated ions. That is not our reference. So the reference is 0. So read out this, that will be the binding energy about 4 eV. Okay? Now that means we have some reasoning for this kind of form that we expect when we see something bind. So this comes to the last page. It motivates the next thing. This is baby level high school covalent bond. So you have atom on the left, A and B atom, when they come together, you see some higher concentration of electrons. So this will attract to this will attract to that. In a way, the electron helps attract the two atoms together, okay? Again, you see the preferred separation, so we are expecting something like that, okay? Now, our quantum mechanics question is as follows. How does such a picture of electron distribute themselves come out from quantum mechanics? Second, how will such a curve come out from quantum mechanics after we solve the Schrodinger equation? Okay, so that is the idea. So let me summarize this first introductory part, and then we'll take a break. Even with this very simple discussion, I want to reinforce your idea that when something binds, we have this kind of curve. Now, that is useful to atomic physics, molecular physics, nuclear physics, particle physics. Okay, you have things that bind. You ought to look for something like that. Secondly, even within this discussion, we involve several things. There is charge transfer to form this ion, meaning we ought to look into how the electron wave functions behave. So that is what we will try to do within quantum mechanics. Otherwise, we don't know how the electron prefer which side, right? Secondly, you see, when we by hand put in the repulsive thing, we already hint at other quantum mechanical effects. We have this anti-symmetric wave function such that electrons, when they live in the same region, they have to think about, I'm spin up, you are spin up, don't come together that close, that kind of effect. So again, that is within the scope of quantum mechanics, how that work out at the end. And we also see that nuclear repulsion should be included as well, okay? So although it's simple, it already hints at a lot of physics that we should handle. So I will stop here for this section, okay? And then now take a break, and then we will continue.